Okay, so now we're going to do limits at infinity. A couple of things you need to be careful about when you're looking at limits with infinity. You do want to look at your end behavior and your asymptote rules. So you want to think about top heavy, bottom heavy, and same degree, as well as what would happen when, when your function is if your function kind of reduces to a line, or if your function reduces to a constant. So we'll talk through all of these as we go. All right, so number 13a. So we're doing the limit as we approach negative infinity. So if we're thinking about our graph, we're thinking about way over here to the left. And all we care about when we're looking at limits and infinity, we really don't care about our smaller terms. So we don't care about our x term, we don't care about our constant. We're just looking at the leading coefficients here on the top and the bottom. So I'm really going to be working with this negative 5 x cubed over x squared. So you guys know that is a top-heavy fraction, and so that means that you would have a slant asymptote. So a top-heavy fraction, really you can work through reducing this, and this reduces to a line. If we do x cubed divided by x squared here, this would really reduce to negative 5x over 1. And that's the end behavior model that we're going to be talking about. And the reason we call the end behavior model is because this messy rational function, negative 5x cubed minus 2x plus 4, all divided by x squared, has stuff going on in the middle. But the ends, way at negative infinity and way at positive infinity, are going to look like this line does. So we can base our limits for positive infinity and negative infinity, we can base on that end behavior model. So what's happening at negative infinity with negative 5x? Well, negative 5x is a line with a negative slope. And so it would look like this. It would go through the origin, but we don't really care about that. We don't care about anything in the middle. We just care about what's happening at negative infinity right now. And at negative infinity, that line would be up high. And so that tells us the limit as x approaches negative infinity for our rational function is positive infinity. That function is going as the x values get very small, the y values are getting very big. All right, we're dealing with that same function at positive infinity for b. So again, we can use that same end behavior model of negative 5x squared, but now we care about what that looks like at positive infinity. So we know at negative infinity it was going up forever. And since this is a downhill line, at positive infinity, this is going down. So our limit as we approach positive infinity is negative infinity. I think the picture really helps. I think it's very easy to get distracted by everything else that's going on. So take that guy, reduce your fraction, and think about what that shape looks like. And this is doable if you end up with x squared there. It's doable if you end up with x cubed. That's why we worked through all of those parent functions and the transformations. Okay, see, our function has changed a little bit. So instead of having an x cubed on top and an x squared on bottom and making a top-heavy fraction, now this has the same degree on the top and the bottom. So again, all I care about are my leading coefficients. So I'm going to grab them and reduce. The x cubes cancel when I get just negative 5. So that's our horizontal asymptote. And that is what this graph is trending towards as we go to negative infinity and to positive infinity. So the limit as x approaches negative infinity of this function is negative 5. So look at those details, take those leading coefficients, and ignore everything else. Okay, more. Lots more examples. All right, letter D. Same situation, but positive infinity. Again, that same in behavior model holds. Towards negative infinity, towards positive infinity, what's happening to this graph is it's leveling out both directions. So, that horizontal asymptote works for both positive infinity and negative infinity. Okay, E and F, now we have to the fourth on the bottom. So the change here is now this has become a bottom-heavy fraction. And you guys know, if we have a bottom-heavy fraction, our asymptote, our horizontal asymptote is y equals 0. So instead of 5, we have y equals 0. That's because the bottom of our fraction is growing faster than the top by a lot. So our fraction is going to get really, 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 really small the closer we get to negative infinity and the closer we get to positive infinity. If that writing out that in behavior model helps you, do it. So I have negative 5 x cubed over x to the fourth. And that's going to reduce to negative 5 over x. And that negative 5 can be distracting. But the thing is, that negative 5 does not matter if x is 1 million. That negative 5 really doesn't put a bearing on it. It doesn't hold the asymptote at all. So here for f, our asymptote is at 0 as well. Remember, the limit is the trend of the graph. Whether it gets there or not is beside the point. Where is the graph going? What is the trend? All right, a couple more examples, and all of these are different. So here we have to be very careful when we're looking for our leading coefficients because they're not always the first term in the fraction. So the first thing I'm going to do here is reorder so I know what I'm looking at. So x squared plus x minus 6 is on top. And in the denominator, I have 2x cubed is my leading coefficient, plus 5x squared plus 6x. And now I can grab those leading coefficients and just work with them. So I have x cubed over x, or x squared over x cubed. So this is a bottom-heavy fraction. And that means our limit is is 0. Our horizontal asymptote is y equals 0. And our limit as we approach negative infinity and positive infinity is 0. Same thing with h. I'm going to reorder so I can kind of get a better handle on my function. X squared plus 9 on top. That doesn't need to be ordered, but the denominator does. 2x squared plus 5x minus 3. So when we're looking at our infinities, everything else becomes negligible. Those numbers become so small compared to our really, really big x values. So here, x squared over 2x squared is going to reduce to 1/2. So our horizontal asymptote would be at y equals 1/2. And our limit as x approaches positive infinity and negative infinity would also be positive 1/2. And that's because those are the same degree. You just cancel when you do your end behavior model. All right, last problem. My function, everything is in order, so I can just look at my end behavior model So my end behavior model here is going to be x cubed over 3x squared. So my x's are going to cancel. Again, the 3 doesn't really matter, but we could write it there. So if my x's cancel here, I'm going to end up with x over 3. And if we're thinking about that as a line, it would be 1/3 x. So what does 1/3 x look like? Well, it's a line, and this is a top-heavy function, so it is going to have a slant asymptote. And this 1/3 x is a line with a positive slope. So 1/3 x, you would go up 1, right 3, if you're being a good little Algebra 1 student and graphing your line. Again, we don't care what's happening in the middle, but I know as my x's get really, really small towards negative infinity, my y's are getting really, really small. And as my x's get really, really big towards positive infinity, my y's are getting really, really big. So now I can't even remember what we were evaluating. We're doing x as x approaches negative infinity. So my limit as x approaches negative infinity is going to be negative infinity. So I'm looking at this part of the line right here. All right, those are limits at infinity, and those are all based on your asymptote rules and your end behavior models. So study those asymptote rules. Keep an eye out for those negatives. That's really what kind of throws things off for you. If you have a top-heavy fraction and you have a negative in your leading coefficient, that's going to be really, really careful. All right, graphing is next.